right, I'll talk about the existential closedness problem for analytic solutions of difference equations. So can you hear me okay? Yeah, okay. So my plan is to begin by explaining what this problem is. And then I'll talk about a one-variable existential closedness result. Mainly for the gamma function. So gamma here is the function, not a value group. And also the zeta function, the Riemann zeta function, but really it's for Dirichlet series, certain Dirichlet series. And then I'll finish by talking about an n-variable existential closedness and some next steps or future directions in this project. So first, this problem, the existential closedness problem, it begins with the exponential function. So existential closedness for the exponential function. And this comes from Zilber's axioms for pseudo-exponentiation. So these axioms, they included two open conjectures about the exponential function. First, Shanuel's conjecture. So this says that if z1 up to zn are complex numbers, which are Q linearly independent, then the transcendence degree over Q of Q with these z's and their exponentials, this is at least n. So this is saying that there can't be too many algebraic relations between these things. So another open conjecture is a counterpart to this, and that's existential closedness. I'll just write EC. So this says that all systems of exponential polynomial equations whose solvability doesn't contradict Shanuel's conjecture all these systems must have Zariski dense sets of solutions. So here we have not too many algebraic relations hold among these things. But if there is an algebraic relation that can hold, then it should hold a lot. So this problem of showing that systems of exponential polynomial equations have many solutions when they can, some special cases have been solved. So some special cases have been solved for the exponential function. But the problem has also been formulated for other functions with analogous versions of Schanuel's conjecture, such as the J function, Weierstrass P functions, and higher dimensional analogs of these things. So this and all these special cases, the motivation for studying these comes from model theory. But recently, there have been results that can be seen as special cases of existential closedness that have been studied by complex analysts and analytic number theorists. So in particular for Dirichlet series.
What do you mean by EC for J?
Right, so it's analogous to this statement. So you're solving systems of J polynomial equations when they can hold. So you have to have some kind of, yeah. Mm-hmm. So recently there was a special case of this problem solved for Dirichlet series, which include like the zeta function. So Dirichlet series, these are sums of the form like this, as functions of S. And zeta is where all these ANs, these coefficients are just 1. And so the motivation for this was studying solutions of, for example, zeta of S equals a polynomial in S. Or specifically, like when P of S is maybe just S, so you're studying fixed points of the zeta function. Yeah, you're right, sorry. Okay. So the people who were studying, they were studying solutions to this equation, showing that there are infinitely many solutions to things like this. But this is just a special kind of polynomial in zeta and S. So you can see it as a case of existential closedness. I'll write their theorem in just a second, but the proof also works for the gamma function, which satisfies this difference equation. Write Z. Okay, so we have special cases of existential closedness for different functions, and I'll write more specifically what this special case is. So this is a theorem of Lee Stoiding from last year. And they actually prove something. Their result is not stated in the full generality that their proof shows, so I'm going to state it slightly differently. So if you have 1 to infinity, an L function like this, And I'm saying L function just to make sure that you have something that's meromorphic in the whole complex plane, a Dirichlet series that extends to be meromorphic. Non-constant. And let P be a complex polynomial in two variables, which is irreducible, and also which depends on both variables. Then P of xy equals 0 has infinitely many solutions of the form, first of the form z comma L of z, and also of the form z comma gamma of z. The proof that they show for L functions just also almost immediately works for the gamma function, so you can write both. And so I'll show you how this proof works because it's pretty simple. So, oh, and I'll do this for gamma. Also, let me call this proof number 1 because I'm going to give a second proof. So first notice that it suffices to find infinitely many solutions to P of xy equals 0 of the form z comma 1 over gamma of z, right? Because if you can always find solutions like this, then clearing denominators, you always get solutions like this. So suppose there are actually only finitely many solutions. Well, then, because 1 over gamma z, it's entire, and it doesn't grow too fast, we can use Hadamard factorization. And so what we get then is that we can factor this as a polynomial. Normally it would be a rational function, but 1 over gamma also has no zeros. Sorry, no poles, times the exponential of another polynomial. But this can't happen, right? Because this side, this is differentially algebraic. This is differentially transcendental over z. So you can't have this equality. So that means it can't be the case that we're able to use Hadamard factorization, which means that we must have actually, we don't just have finitely many, we have infinitely many solutions to.
Why is that so? Why does it satisfy the differential equation?
Why does this satisfy a differential equation?
Why the one after the
Yeah, polynomials, yeah. Yeah, right. So this has infinitely many solutions because we can't use Hadamard factorization. So a couple of things. This proof is nice. It's quick and simple, but there are a couple things maybe that we would want from a proof of a result like this that this doesn't do. So first, because it's a proof by contradiction, it doesn't tell us anything about the distribution of our infinitely many solutions. These authors, when they prove it for Dirichlet series, in the specific case of the zeta function, they can use Neven-Lino theory separately to analyze the distribution of the solutions. But I'm going to give a second proof that allows us to better understand how solutions are distributed for gamma. And so the second thing is that really we want to study systems of gamma or zeta polynomial equations in many variables. And this proof only works for one variable because there's no higher dimensional analog of Hadamard factorization that we could use. So I want to talk now about a second proof of this theorem, which is joint work with Sebastian Eterovich, which I'll prove just in this same case. But the point is that we use different techniques that will generalize to higher dimensions and which do give an idea about the distribution of the infinitely many solutions. So that's my goal now for most of the rest of my talk. And the proof idea here, this proof idea was simple. And this proof idea, it's also simple, but it takes a little bit more setup. Okay. So I'm proving the same theorem. And first observe that it suffices to show gamma of z equals an algebraic function. So this is, maybe I didn't set this up. So here a was a polynomial. Here I mean it to be an algebraic function. So it suffices to show that things like this have infinitely many solutions. It's like, so you have a, yeah. Okay, right, and you can reduce to this case, right, because we're trying to solve polynomials like this, so you're just sort of rewriting it in some way so that you can isolate gamma. That's the point. And this is maybe a slightly simpler form that will be easier for us to analyze. So Hadamard factorization doesn't have a higher dimensional analog, but we'll use the argument principle, which does have an analog in higher dimensions. Principle. And so just to remind you what the argument principle says, maybe I'll go to a new board. So this says that if you have C, which is a closed C1 curve in the complex plane, then the winding number of the image of C under this function gamma minus A, because we're looking for zeros of, say, gamma minus A, around 0, this is equal to maybe I shouldn't have. This is equal to the number of zeros of gamma minus A inside of the curve C, the closed curve C, which bounds some region, minus the number of poles of gamma minus A inside C. Move it down again. Right, we can think of it, just work outside of some disk where A has all its poles and zeros. And we also want to work really in the right half plane where gamma doesn't have any poles. So the curves that we consider will always be, sort of up to the left enough that you don't really have to worry about poles anyways for the curves that we'll be looking at. But this is generally what the argument principle says. All right, here I wrote it for gamma and A. But so the goal. Yeah, right. In C, right, in the region. Yeah. Yeah, I guess I should say maybe inside C. I don't know. Interior, it doesn't matter. You understand. So the goal, the way this proof will work, is that we're going to find infinitely many curves where, again, we don't have to worry about the poles of gamma or A, which have non-zero winding number. Each curve will give us at least one zero of the function. So if we have infinitely many of these curves, then we get infinitely many zeros. Okay, so before I tell you what these curves really look like, let me I'll just draw like a schematic picture of what the curves should do. So maybe we start, our curves, I want to divide it into 4 pieces, so I'll draw it like a rectangle. So this is the curve C, and I'll label the sides 1, 2, 3, and 4. And I want the image of this curve under gamma minus A to look like this. So first 1, I want the image of 1 to be some kind of thing that's far enough away from 0, but still kind of small. But maybe it looks funny, it does some weird things. So this is like what 1 is. 3, I want this to be some kind of big circle-like thing. So like this is 3. And then 2 and 4 are just connecting the edges of 1 and 3. So maybe like this. And so notice the way I've drawn it, the winding number of this curve around 0 is 1. And that's kind of because I've arranged it in such a way that this squiggly 1 part is over here. The endpoints of the image of 3 are kind of on the opposite side, and 2 and 4 pass from 1 to the endpoints of 3 around 0 on the same side. So I'm drawing this curve in a suggestive way, and I want to try to figure out enough about the gamma function so that I know what this curve has to actually look like in the complex plane to make this picture. So, okay, maybe a little bit more specifically. On 1, I want the modulus of gamma to be really small so that gamma minus A is basically, it behaves like minus A. on 3, I want the modulus of gamma to be really big so that gamma minus a behaves just like the gamma function, so it has to be much bigger than a. And then on 2 and 4, well, like I said, I want them to pass kind of like on the same side of 0 when, if that makes sense. Okay, so in order to figure out what this picture needs to look like, we need to know a little bit more about the gamma function. So there's an infinite product representation of gamma due to Weierstrass. So you can write the gamma function as, what is it, e to the minus gamma z over z times an infinite product, 1 e to the z over n over 1 plus z over n. It's a little cramped, but I'm kind of just writing it down to give you, because it's useful in figuring out what gamma does on this, on the complex plane. And just to give you a sense of what gamma, I don't know, a better sense of what it looks like. So, oh, sorry, yes, the little gamma is the Euler-Mascheroni constant, which is about 1/2. Mm-hmm. Yeah, but it's a specific number. Okay. So first, it's easy using this representation to show that for y positive, and for a fixed x positive, the limit as y approaches infinity of gamma of x plus iy is 0. And if you look at the modulus, then it approaches 0 monotonically. So this is saying, for some like real parts, go up along vertical lines, and then the modulus goes to 0 monotonically. And we can also say, using this formula, what happens along horizontal lines. So for fixed y, the limit as x goes to infinity of the modulus of gamma plus iy is infinity, and it goes to infinity monotonically for x bigger than some number alpha, which is about, it's like 1.46 something. This alpha, it's the positive real, the unique positive real 0 of gamma prime. But you just have to go a little bit far, and then this limit goes to infinity monotonically. Now, understanding how the gamma function behaves on horizontal and vertical lines, or half lines, is enough to tell us what the curves of fixed modulus look like. So let me write that. So the curves of fixed modulus will look like this. So for a real number, positive real number, the curve modulus gamma of z is equal to r. This defines a single C1 curve with positive slope as long as we restrict ourselves to this like upper right quadrant with x bigger than that number alpha. So I'll write Q for quadrant alpha, which is the set of z such that the real part of z is greater than alpha, which is like a 1.46, and the imaginary part of z is positive. So why is this? I'll just drop a few pictures. First, we're able to use the implicit function theorem to write the imaginary part of z as a function of the real part on these curves. And now, why does the curve defined by y have to have positive slope? Well, if we think about those two lemmas, if you have, maybe, let me go up a little. So here's some number z that's on this curve, this curve, and in this region. Then as you go up vertically, the modulus of gamma goes to 0. And as you go horizontally, the modulus of gamma goes to infinity. It's increasing. So the curve of fixed modulus has to go somewhere in between like this, positive slope. And oh, and I only wrote part of that lemma that I wanted to prove. So and the curve has no horizontal or vertical asymptotes. So why is that true? Well, suppose you had your curve and it had some vertical asymptote. Well, if this is the curve of points whose modulus of gamma of z is equal to r, and if the modulus always increases going horizontally, strictly, then along any horizontal line like this, the points over here, gamma of them have modulus strictly greater than r. But on the other hand, along this vertical line, the modulus should be going to 0. That can't happen if the modulus is always strictly greater than r. So you can't have vertical asymptotes. For the same reason, you can show there's no horizontal asymptotes. And for the same reason, you can show that there's just one of these curves of fixed modulus r for each r. And now, once we understand the curves of fixed modulus, you can understand the curves where gamma has fixed arguments. So for each theta in 0 to 2 pi, the equation argument of gamma of z is equal to theta. This defines countably many disjoint C1 curves with negative slope. So the picture of these curves of fixed positive and of fixed modulus and fixed argument for gamma in the complex plane, or in Q alpha, this like upper right quadrant, looks like this. So the curves of fixed argument, I can use colors. So the curves of fixed argument, they look something like this. Sorry, fixed modulus. And the curves of fixed argument look like this. And also the argument repeats, so maybe say these are all the curves where the argument is theta, say. And so if we want to find some kind of curve that does this, well, number one, that piece of the curve is where gamma should have small modulus. So maybe it's some fixed modulus piece pretty close to the left where the modulus is smaller. So maybe this is where 1 should be. 3, the modulus of gamma should be really big. So maybe it's some fixed modulus curve where the modulus of gamma is big. And then 2 and 4 just connect 1 and 3. Oh, and so also we want to have a full circle. We want the image of 3 to be like basically a full circle. So the argument should make a full circle along the length of this curve 3. And then maybe we connect 1 and 3 along curves where gamma has fixed argument. So this is maybe what C should be. And I'll show you why that works. Here. So, no, maybe I'm going to get a new board because I want space to draw the pictures. Oh, no. I don't want to erase the theorem. Okay, I'll erase this one. Okay. I won't erase that quite yet, just so you can keep it in mind for a sec. So let me just copy out sort of that curve C, but a little more neatly. Oh, and this is a proof sketch of the theorem up there. So here's 1, 2, 3, and 4. And the image of this under gamma minus A, well, if we pick 1, oh, and let me also assume, just so that I don't have to split into different cases, assume that as the modulus of Z gets big, the modulus of the algebraic function also gets big. This is an assumption you can deal with without too much trouble, but it just takes a little bit more work to be able to do the same argument when this doesn't happen. But assume this for now. Then, because we're assuming that the modulus of the algebraic function goes to infinity, as long as we take this curve to be kind of like high enough in the upper right quadrant, that means that the image of 1, if we assume that the modulus of gamma is less than, say, 1 on this curve, will be basically like, it's like 1 minus A, roughly, or like basically like minus A if A is really big. So we can assume that the image of 1 under gamma minus A is far enough away from 0. And we can also make sure that it's like relatively small, because the length of this curve we can take to be relatively small. So here's 1. The image of 3, we're assuming that the arguments of gamma makes a full circle from here to here. And let's also make sure that the modulus is much bigger. The modulus of gamma is much bigger than the modulus of A along this curve. And then we can sort of choose it to make a big circle. And I'm allowed to draw this opening over here kind of opposite from this part 1 because we can take these curves of fixed modulus, we can sort of shift up or down slightly between these curves of fixed, we can take these curves of fixed argument, we could shift them down, up or down slightly between the curves of fixed modulus to arrange that the argument of gamma is opposite from wherever this one piece is. So here the argument of gamma is some fixed number theta for appropriate theta. And it's the same theta for both these curves, so that we make a full circle as we go along number 3. And then they connect like this, maybe. But the problem is, what if 0 is sort of between them? Well, if that happens, there's an easy kind of parity fix. Which is just to repeat the same argument, the exact same argument again, with another kind of curve stacked on top of this one. So if we now have 2 of these curves, I'll label them differently. So here's A, B, C, and D. And these fixed argument curves are, let's say, 1, 2, and 3. Then the image of this under gamma minus A. Well, this bottom one maybe makes this same picture. So you have some squiggly part. This is A now. And this is this big circle is D. And then 1 and 2 maybe go like this. But then B is just another little squiggly part connected to A. C is just this is a B down here. C is just another big circle. So I won't draw it again, but C, well, okay, I can draw it again. So C just goes around again. And now what has to happen to this number? Oh, sorry, this is 2 and 3. This should be, okay, 3. What has to happen to number 1 up here? Well, it connects this point here to an endpoint of C over here. And it has to pass on one side of 0. Just, it has to, right? Or it can go through 0. And then you have a 0 of the function, and that's great. So let's say it goes on this side. So let's say 1 is over here. Well, then redrawing this picture a little bit more neatly for this top rectangle. Well, here's B, here's C, here's 2, and here's 1, and 0 is inside the curve. So its winding number is 1. So now we found a 0 of gamma minus A in the interior of this curve. Okay, and now we can just repeat this argument, looking back at this picture, just keep going up, and we get infinitely many of the same kind of curve, and we can find infinitely many zeros of gamma minus A. So I should mention that this idea of using the argument principle to find solutions for existential closedness problems, this originally came from a paper of Vahagan Aslanian, Vincenzo Mantova, and Jonathan Kirby.
So
Yeah.
in the 2 and 4 argument exactly that, or you're allowing it to move a bit?
Well, I'm sort of adjusting it if I need to make sure that these 2 endpoints map here, which is opposite of this thing. But once I adjust appropriately, then I fix the argument. Then I fix theta. Is that okay? Okay. Right. So the purpose of this is that there's a higher dimensional analog of this proof. Yeah.
The argument of gamma z is not the same, or is it the same?
It's the same theta. Yeah, it's the same.
Theta. So why are they on different lines?
Because the argument of gamma will repeat, right? Just like the argument of the exponential function repeats as you go up, right? So this gamma is not like literally periodic, but it does have a repetitive behavior that we're able to exploit in order to use this. That's actually one of the points that I wanted to make, is that all the existential.
Right. You drew the countably meaning.
Yeah. Right.
Not very
Mm-hmm.
same theta for all the squares.
Yeah. Yeah. But right, so other existential close, this problem has been studied for functions that are periodic, and the proofs use the periodicity. But this one sort of uses the fact that you can still have some kind of repetition without periodicity by using this parity argument, which is a simple fix. Right, and the reason why Sebastian and I wanted to use the argument principle rather than the original proof that these people gave is because there's an analog in higher dimensions. So let's say, I won't write it out, maybe. But let's say we have a two-dimensional case. So now we have a polynomial in 4 variables, x1, x2, y1, y2. We're trying to find solutions of the form z1, z2, gamma z1, gamma z2. If we assume, I'll write it out. I should just write it. So let v in c to the 2n, for n bigger than 1, be irreducible with no constant coordinates and with dominant projection onto the first n coordinates. Then V has a Zariski dense set of points of the form z1 up to zn and gamma of z1 up to gamma of zn. And so here I'll just sort of say roughly how does this generalize just for n equals 2. So the picture is that now, because we're assuming that the projection is dominant, this reduces to solving systems like this. So gamma of z1 is equal to, again, some algebraic function, this time of z1 and z2. And gamma of z2 is some algebraic function of z1 and z2. So call this star. So we want to solve things like this. And roughly the idea is now we want to take like 2 kinds of these curves that I drew here, so that the region bounded by the first curve be omega 1. Let the region bounded by the second curve be omega 2. And we want to show that the higher dimensional analog of the argument principle is that the boundary of omega 1 cross omega 2, which is, so it's not just the product of the boundaries, it's the boundary of omega 1 times omega 2 along with omega 1 times boundary of omega 2. So we want to show that the image of this under this system of equation, or this, move everything over to one side, looks like roughly like this. So you have some big hypersphere, and then you have some smaller thing that's like a hypersphere, and you have some tunnel connecting them. And we want to make sure that 0 is not in the tunnel. That's roughly how this goes. And so this kind of thing will generalize to higher dimensions, and roughly by doing the same argument, but simultaneously n times if you're in n variables. And
is the image of dimension complex dimension 1 or 2?
This is complex dimension 2. This is a picture in C4 that's drawn, That's why I was saying like hypersphere, but I didn't so this is like a hypersphere. This is like a smaller thing, Dimension. That's in fact another point that I wanted to make. So here I said let this be less than 1, but you can in fact compute a number r less than 1 that works given a curve gamma, or given an algebraic function, or given a polynomial or algebraic function, and some place where you roughly want to start. You can also say, instead of just being bigger than this, you can say let this be some large number r, which you can also calculate, which is bigger, much bigger than the modulus of a of z. This argument, you can also calculate exactly what it needs to be. And so you can do all this.
But this changes, right? The a of z, the modulus of a of z goes to infinity.
Right. For each curve, it's a different, a different number. But for each curve, you can calculate exactly what it needs to be. And then you just say, okay, here's my starting point. Here's some curve that's slightly out of here. And so I can calculate what these numbers need to be. Here's some other further out starting point. And again, I can calculate what it needs to be. Yeah?
But I think you're going to say what is the high-dimensional realization principle? What is like one number, for example?
Yeah, so it's a little bit more complicated. Here, all we really need is that 0 is inside of the region bounded by this thing. Yeah. We don't need the full strength of the argument principle in higher dimensions. Yeah.
More than the risky bands, right? So it's somehow distributed in a certain way.
And these are great questions, because that's also a point I wanted to make, is that really where the infinitely many solutions are, they lie in this sequence of rectangles going out exactly in this way. And even in higher dimensions, right, you can sort of tell again where exactly the solutions are. Right. I was going to write these notes down of observe this, and observe, but okay, everybody has questions. So, right. So, the last thing maybe I want to say is that, so these next steps, I started by saying existential closedness is you should see it as a counterpart to Shanuel's conjecture, which is a transcendence result. We're hoping next to study functional transcendence for the gamma function. So get some analog of aix-Shanuel for the gamma function. So that's one thing we're hoping to think about next. And that would be kind of different, because these other functions for which the problem has been studied, they're solutions of differential equations. So here we want kind of some difference aix-Shanuel, which is something that hasn't been done before.
So do you have a general result for some solutions of different equations, or just for gamma? No.
Just for gamma. I titled my talk Solutions of Difference Equations because really I kind of think that this should work. The point I was trying to make with saying gamma is not periodic, but it still has some kind of repetition that allows you to do this, is that maybe for other solutions of difference equations, you should again be able to kind of exploit some kind of periodicity that comes from the difference equation and do the same kind of argument. Mm-hmm. Right, so then other kinds of difference equations. So one example is so I would also like to study existential closedness for a function that I'm interested in, which is this function satisfying this difference equation, which on the real numbers, it grows trans-exponentially. And it's also, it's analytic on the complex plane minus the real numbers less than or equal, less than or equal to -2. So it has this extension to the complex plane, and because of the difference equation, I'm hoping to exploit the periodicity, not periodicity, but some kind of repetitive behavior with this kind of thing. And I've been talking just very recently with Vincenzo Mantova about possibly proving some kind of existential closedness for this function. Okay, so I'll stop. What?
Or disproving it.
Or disproving it, right. Yeah, disproving it. Oh, one last point. We know because of this, right? Okay. So the gamma function is O-minimal on the real line, but it's not known to be O-minimal on a complex domain. So in order to prove ax-shanual for gamma using the kind of O-minimal techniques that have been used before, and you might want to know that gamma is O-minimal on some region of the complex plane, and that's not known. So that's another kind of interesting thing that would be useful to know more about. Okay, I'll stop there.
Okay, questions?
I'm not sure what you said exactly, but do you actually show that the set of solutions has the part that the distance from each other is finite? That it's finite? Do we get you can cover the plane with solutions up to bounded distance?
Yeah, right. So as you go up, the length of these sides of the rectangle is actually slightly decreasing.
Even
So-
decreasing?
Yeah, so actually the solutions are getting closer and closer together.
I see. So there's some fixed radius such that you take a set of solutions and you take the union of the ball of that radius, you just cover the plane.
Yeah.
I see. Great.
So may I ask, so you mentioned Hi. May I ask, you mentioned that there need to also be some kind of condition that we only need to look at system that is allowed by the analog of the Shanual conjecture, but how does it reflect in this picture?
Right, so the assumptions here of having no constant coordinates and having dominant projection, those are things that should always have solutions. So that kind of takes into account that there are some that, of course, won't because there's some kind of algebraic relations. I mean, some kind of transcendence that prevents you from having solutions.
I see. So is it fully verified existentially closed theorem for this type of gamma function?
Okay. Also, these assumptions maybe are too strong. So there could be more kinds of systems of equations that we don't know how to solve, but where you should have solutions. Really, to know exactly when, we would really want to formulate this theorem.
Okay, more questions?
So just in terms of this, so the special properties of gamma are the blue lines really that are fixed?
The blue lines are all fixed argument curves.
And
you
this comes out of the difference equation, basically, or because it's very soft. It seems soft relative to gamma. You don't use much, but so.
Right. So we use a little bit that I erased it, but the product formula for gamma, which is a little bit more than the difference equation, to prove those first two lemmas which I erased, that about behavior on vertical and horizontal lines. And just from that behavior, then you are able to know all this that you need to know about the fixed modulus and argument curves.
Okay, so let's thank the speaker again.